Hello. In this video, I'm going to be working with axial loading, another statically determinate problem. This is actually the last statically determinate problem. It is the most complex because it's a composite problem. So, as we can see here, we have the shaft with a clamp on the left end, uniform geometry with two different loads on it. Notice that we're working with SI units. The outer material, which is the green, is aluminum with a Young's modulus of 70 gigapascals, and then the inner material is steel, which is 200 gigapascals. Then we have the inner and outer diameters. So really quick, I'm going to go back. In the program, if you go to help Determinate, you can get to this PowerPoint, and these are all the equations that you're going to be working with a composite problem. So kind of the idea of the composite problem is, well, you have two different materials, and that means that the reactionary load, the axial force, is going to be spread out between the two different materials. So you can see here P is the total, and it's a summation of the outer and the inner reactionary loads. And you can see here are the equations for those outer and inner loads. One very important thing to notice is that even though the outer and inner material will have different loads, which is, mainly a function of their different Young's modulus and their own area. As you can see here, just looking at the equation, you can see for the inner reactionary load, the numerator, you have its Young's modulus and its area over the summation of the total Young's modulus times area. So even though those reactionary loads are different, and then following that, the stresses in the outer and inner material will be different, the elongation for the shaft as a whole will be the same. The elongation of the outer material is going to be equal to the elongation of the inner material. Now, this does mean that if you're only considering finding the elongation or compression of the shaft, you could just choose to work with the outer and inner material. You could say, okay, here's my total load, then solve for the inner material reactionary load, and then you could use that to solve for the elongation, and that should come out to just be what it is. And then you could choose to resolve it looking at the outer material and see if you get the same elongation. If you come up with a different elongation, then you know that somewhere you made a mistake, because both of those elongations should be the same. So that's kind of the main idea behind it. So we can start working on this problem. One thing I wanted to mention in this video is, I know I mentioned it before, but the difference between segments and sections. So as you can see here, right when you start the program, it comes up with the segments little box, and it tells you about it. Basically, a segment is a section, well, I guess segment has uniform geometry. As soon as the geometry changes, you can consider it a different segment. The difference between segments and sections is that sections also consider loads. So just looking at this problem and ignoring the loads on it, the geometry is uniform entirely through. So what we can say is we can just say number of segments is only one. And then later we will add in the loads, and it will bring it to two sections. What I've done in the past problems is I have just treated sections and segments as the same thing entirely. So even if it was uniform geometry, I knew that it was going to be two sections, so I broke up the segments the same. So then the end of the segment was exactly with the end of the section, and so on. This is just another way you can think about it, though. So we can start putting in our information for the shaft. It's composite. Total length is 400 millimeters plus 300, so that's 0.7 meters. Outer diameter, 50 millimeters. Remember to put everything in base units. Outer modulus for aluminum, 70 gigapascals, which is 10 to the 9th. Okay, now the inner material is steel, 200. Enter that in. And here I have solved for those corresponding areas. Okay, so now we can start putting our forces on this. Max number of forces, we only have 2. So just as usual, force 1 working from the left, 45,000 newtons in compression because it's towards the clamp. And this is at 400 millimeters across. So 0.4, it's 45 negative because it's compression. The other one is at the very end, and it is 70 kilonewtons, so 70,000 newtons. Positive because it's in tension, it's pulling the shaft away from the clamp. And this problem is clamped on the left. Okay, now it details you about sections. It involves everything a segment does, except it also looks at force. So just as we had earlier, we have one segment and 2 sections. And that's because you have this load on here, one section, new load, so it's a new section following that. And we can draw it. And down here at the bottom you can see it's more or less what our problem is. So, working from the right, we can analyze section 2. Now, aside from using, the main difference in composite problems is that you have to solve for the reactionary load of the inner and outer material, and that's more or less the very main thing. Just some of the equations are a bit different, and just to be thorough, you're basically solving the information twice, because you can solve it for the outer material, then solve it again for the inner material, and so on. So this is just looking at section 2. I have it all written out. Now, section 2, you have 70 kilonewtons on the right end. Summation of forces, that means the reaction has to also be 70 kilonewtons. And you can see how this follows. You have, at least for the outer material, you have your 70,000 times the outer Young's modulus times the outer area over kind of the total. And it's the same for the inner, except in the numerator you put in the inner Young's modulus in the inner area. When it comes down to stresses, it's basically the same equation, except you omit the area in the numerator. And especially when you get to delta, the elongation, notice they both come out to the same value, as they should. So we can put this in. outer force the outer stress, and when it comes to composite, I guess there's another level of complexity, because even though the elongation is strictly the same, I mean, you also have to worry about the different stresses involved in the different materials and what they can handle and so on. So stress outer is times 10 to the 7th. Okay, the inner stress it's more than twice what the outer stress is. Okay, and now the elongation. Doesn't matter if you put in the outer elongation, the inner elongation, they're the same. That value is okay. We hit check. Looks like those values are all right. Now we can move on to section 1. Same exact type of analysis, same equations and everything. The only difference is now in section 1 we have also that 45,000 Newton load in compression. So it really just comes down to summation of forces. Now our reactionary load for sectionary 1 is only 25,000 newtons. Plug that into the same equations, follow the same process, and you will find all of your information. So our outer force our inner force, outer stress, and our inner stress, finally the elongation. It's a very small amount. That's because this compression is working against the tension. Smaller reactionary force total. It's a very small number. Okay. Solution complete. And you can notice our net elongation, which is in meters. It's a very, very small amount. What is that? Almost 0.2 of a millimeter. Very small. Okay, so that's more or less it for how you work with composite problems. The process itself isn't very different. It's just a bit more number crunch heavy because you're working with slightly changed equations, but also you have to solve for a set for the inner and then the outer material.